Okay, we should be live. Okay, so today I just thought that we would continue going through the list of open problems and see how to clean them up, and probably some of them are gonna be things to delete. And the next time I was thinking that I have a bunch of stuff that I'm doing for generalized ensemble spaces that it's a lot of it's ready for review. So I thought maybe we just go through it here and review it. It's something that basically puts together a lot of ideas from information theory, convex spaces, measure theory, just puts it all together. So the goal is to find a single mathematical structure that we can use to do all the things that we need in physics. So that's really nice. And I already have other people on the math side that are helping me looking at it. So I think it might be just worth to go through the whole thing. So for today, let's just go through. I need to share. I think last thing that we talked about was the product of observables. And there it is. I actually talked to a mathematician just a couple of days ago on the problem of products of observable, and he was just confirming that we basically do not have it's still an open problem to understand what these things are. He was also making me notice that similar things are there even for the sum of observables, in the sense that yes, we know what the operator is when you sum, but going from eigenstate of eigenvalues of the two operators that you're summing to the eigenstates and eigenvalue of the new operator of the sum, it's completely non-trivial, and we don't really have any insights that might make that understanding easy. So yeah, that's interesting to me how a lot of these things that have been there for a lot of time, they're still not so well understood. Anyway. The next one is probably very technical, and it's find correct morphisms for the experimental domains. So in the book, in our framework, we have this idea of an experimental domain being a bunch of statements that are experimentally verifiable. And you prove that experimentally verifiable statement have to follow a certain logical structure, and you create um, these objects that are these experimental domains. And what it would be nice that I've never done, it would be to give it sort of let's say, a category theory treatment and understand what the morphisms in the category are. And the issue is that these things typically become um, topological spaces. So these mathematically, the set of verifiable statements become a set of open sets. And there are different categorical things that look like that. There are things like locale and topos and stuff like that that are, in some sense, similar. The issue, from my understanding, is that all these objects have a different type of morphism defined, so a way to relate one space to the other. And so to be able to compare exactly what is the structure that we need compared to the one that are already used in category theory, one would need to understand what is the right type of morphism. And this is something that, in some sense, is interesting to me, but in another sense, I have other things that I'd rather do. So it's an open problem. So find the correct definition of morphism over the current definition of experimental and theoretical domain. And a mathematical problem, currently the only maps we have defined over domain are experimental relationships. And experimental relationships essentially are things where you have two domains and you know that sort of one domain tells you what the other domain is. So, for example, if you know the temperature of water, then you're going to be able to reconstruct the water density, but not the other way around because there are different water density. The same water density can be achieved with different temperature. And so you have this domain that is a function of the other domain, that there is a dependence. And I don't have a morphism instead for that it's more general, where things are maybe are related or there is some relationship, but not a full causal relation. And so the idea is to find a more general definition for morphisms, math-preserving structure. This should recover, for example, the domain product is a categorical product, and we suspect the categorical product and the co-product will coincide. This is something that is a conjecture in this space. One direct constraint is that they need to preserve logical structure. Therefore, they will, for example, preserve narrowness. So if a statement is narrower than another one, when you map them, that should be also the case. And narrowness is in some sense similar to implication. So if you have something that implies something and you map the statements, then the new thing that is mapped should imply the other one. And but the issue is there. Okay, so we have to preserve narrow, but the issue is that the domain and codomains are not disconnected structure. They are embedded in a single overall structure. And the domain product, for example, uses the overall structure when closing over conjunction and disjunction. This is very technical. If somebody hasn't seen this structure, this makes absolutely no sense. Therefore, the morphism should not only preserve the structures of individual spaces, but also preserve consistency within the overall structure with the overall structure. The current hunch is that the map from one domain to the other should map to the narrowest broader statement. Yes. The current hunch is that the map from one map to the other maps to the narrowest broader statement. Yes. And Cram says, if we're dealing with topological spaces here, it might also be valuable to check out condensed mathematics, which I have no idea what it is. But that stuff is brand new as I understand it, so probably still highly technical. Okay. Yeah, this is where I basically need a person who is already an expert to talk to them, probably even just an hour, and the things would be settled. Okay, so the idea is if we have a domain dx and a domain dy, then a morphism is a map from dx to dy such that if Sx is narrower than Msx, which is narrower than Sy, for all Sy, right, so you get the Sx is narrower than the one that is mapped, and it's also narrower from Sy for all Sy for which Sx is narrower than Sy. So you basically move to something that is narrower than any other statement that is already broader than Sx. And so that could be the hunch that this is the correct morphism. It may be that this is the only requirement needed, and the preservation of the structure across the map would be a corollary. We can also think to perform such morphism in the whole context. In this case, the morphism should be idempotent. It would basically project the whole content to the domain. One thing to keep in mind, therefore, is whether this type of operation will then be related to the projection in linear space. So this is essentially something that might justify a lot of other things at higher level. And so it's why it should be interesting to look at it. And Cram says condensed mathematics and the notion of liquid tensor are a project by Peter, I don't know how to pronounce it, to make topological spaces more amenable to category theoretical techniques, as I understanding. Okay. Yeah, I always wondered why, like a lot of people who do locale and topos and all of that, they have a structure that basically is always can always be shown to be mapped to topological spaces, but then the thing that they construct on top of it, they seem different from what you do with topological spaces. I never quite understood, but again, I never even spent so much time to looking at it because I am busy with other things. Okay, so that's the math. The physical significant, the idea here is to understand what it means conceptually to map from one domain to the other. We found that constructing a product domain means putting together two different sets of experimentally distinguishable aspects. For example, horizontal and vertical position of a body, density of water and temperature of a mercury column in thermodynamic equilibrium with it. Here we're asking what it means to map from one domain to the other. The domain product combines the information we can experimentally obtain with different domains into a single domain. This will work differently depending on the degree of dependence of the domains. In fact, the type of product, the domain, can be used to characterize the different cases, the dependence between the two things. If X and Y are independent, for example, all combinations are possible, so the whole XY plane is possible. Conversely, if Y depends on X, given a specific value of X, there will be only one possible value. Here we're most likely trying to characterize how much information can be learned about one domain from the other. For example, if the horizontal domain and vertical position of the horizontal and vertical position of the particle are independent, then a statement about the horizontal position will tell us nothing about the vertical position. And so mathematically, any statement on the horizontal position should map to a certainty in the vertical position, to map to every possible case because you can't know anything. Conversely, if there is a correlation, then we should expect to map to the statement that provides the maximal amount of information given the constraint that should map mathematically to the narrowest, the broader statement. As I said, this is kind of the things that I feel that if they're done correctly at a foundational level, they would be recovered in higher level structures when we are looking at the things that maybe physically are more interesting than just the logical statements. So, and I also think that since it's about information, probably there is going to be something both measure theoretic and information theoretic as a consequence of all this. But so anyway, this is an open problem, and I think it's already well characterized, or it's cryptic for people who don't know this stuff. But again, that's how it is. Then the next one, characterize the space of domain relationship. Yes, this is something that it's basically a problem in topology. And so characterize the set of all possible topological relationship between experimental domain. Again, we have two experimental domains, so something about position and momentum, vertical direction, horizontal direction. You put them together. You have the joint domain of statement of things that you can say about these things. And you want to know all possible ways that two things could have a joint relationship. So they could be independent, they could be very dependent, they could be in which way they can be dependent. And this is a problem that I don't have. And maybe it's just trivial topologically to solve, but again, I haven't spent so much time to look at it. So the problem we're trying to solve makes more sense in terms of our general framework, but let's try to formulate it in plain topological terms. We have three topological spaces, X, Y, and Z, all of them second countable and T0. Z is a subspace of the product space, meaning that we have a continuous transformation Fx to X and Y. It is also the case that all open sets of X and Y are traceable from Z, in the sense that every open set UX can find an open set UX such that UX contains and only contains all X in X, and such that X and Y is in the image of that for some Y. So that's basically what I'm looking for, and I don't know if it's an embedding, an immersion, or some stuff like that. I have no idea. And so given that given X and Y, we want to characterize the space of all possible Z with the previous relationship. And the physical significance is that the idea here is that each topological space represents a set of possible experimentally distinguishable cases, and Z represents the joint cases of X and Y. And if X and Y are independent, for example, all combinations are possible, so the whole XY plane is possible. But if a Y depends on X, then for a specific value of X, it will be one and only possible value of Y, and F must be continuous. And the idea that there should be a whole set of in-between cases, and we want to characterize the space of these cases. So you might have some correlation, so some relationship. If I tell you X, you know something about Y, but not everything. If you know Y, you know something about X, but not everything. And that's still topologically going to be something, and yeah, and that needs to be still. This is still an open problem, and I have no idea. Okay, more in-depth exploration of coordinate invariant measure. Find if there are more mathematically interesting and precise way to express the idea of invariant measure. Okay, so this is something that relates to the fact of um, what they called what phase space is essentially. It's we are able to recover phase space by basically saying we have a set of variables and we want to be able to put an invariant density or an invariant entropy on that, meaning that we can change coordinates, we can change units and the number of states, the entropy, the probability density for each state does not change. And it works at a physical level, but the issue is that we don't have a tight mathematical way to express what a unit system is. And it's kind of sad to me that we don't have it. That it just mathematically, we just ignore the units and we just look at the numbers because the units are very important. And also because the units end up to actually give this structure. So we have the thing intuitively and we know that it works. We need to make it mathematically more tighter. It would be nice because then we would basically mean that we have a good theory of unit systems in math. Okay, so mathematical problem in our derivation of classical mechanics, we recover symplectic spaces by requiring that the measure needed to quantify the number of states in a region must be coordinate invariant. That is, we need to be able to change the coordinates while keeping the measure invariant. This leads to the need for a conjugate quantity such that the dq wedge dp is equal to dq prime dp prime. So if you change the units of q, then the unit of p changes in exactly the opposite way, such that the total remains the same. Okay, question, but how can we have an invariant that doesn't produce fraction in some units? Seem impossible. So the idea, it follows like this. So let's say that you have meters. Very good. So one variable is meters. If the other variables that you have is inverse meters, when you try to make the area, whatever you have in units of meters gets canceled out by units of inverse meters, and now your area is invariant. And so if you change from meters to feet, then the other quantity will change from inverse meter to inverse feet, but the product remains the same. So that's basically the idea. And again, this is the intuition, and then it's the thing needs to be specified. And so it's invariant in the sense that if you change the unit system, that unit that was measuring the area, it's independent of what unit system you chose for the units of the variables. That's the idea. And so the question is whether we can formulate this requirement in a more abstract way, since our theory, quantum mechanics, must have similar requirements. e.g., for differential manifold, there is the idea of generalized complex structure. And I think actually the right thing here, it might be the Poisson structure, because that's what e.g. Both quantum mechanics have a Poisson structure that becomes the Poisson brackets in classical mechanics and the commutators in quantum mechanics. This is also probably related to the generalized complex structure. So the idea of this invariance, it's essentially what gives us the the symplectic structure, the pairs of variables, the Poisson structure, the fact that quantum mechanics is in a complex vector space instead of a real or quaternionic. It's because you have this structure here. And so if we were able to encode this mathematically precisely, then we might be able to say that a generic state space that has this feature has this structure, and then you recover classical mechanics and quantum mechanics because you have this structure. So, so that's sort of the piece that I'd really like to abstract is that. So one way to approach the problem is to see what properties measures possess on the complex plane. This might be related to understanding why integration of the complex space is more powerful than the real line. And I, 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 I hear mathematicians saying that. I still don't understand what it means. And trying to justify those properties from the physics may lead to new ideas. That's basically what we want to try and do. And the physical significance, the requirement of coordinate invariance measures stems from the principle of relativity and the idea that nature must account for preservation of number of states during deterministic and reversible evolution without specific reference to reference frame. So this is basically what you're trying to make invariant here. Like you basically want to say, okay, there are states, and we are going to characterize states with variables that have units. But the units that we use to characterize states are not, um, let's say, actually, the way that we can characterize the things like determinism, reversibility, probability over states, and all of that should be something that does not change based on, that does not depend on the units that, particular units that we've chosen. And again, this makes it's a simple and intuitive to say, and we can sort of do some, physics, topg, podgy derivation, but I don't have a way to formalize this mathematically in a tight way. That's what this thing is about. And here we want to find the most minimal and general mathematical argument to that effect so that we can have that. Okay, I agree in theory and intuition, depending on the size of our unit, our ability is limited by units we chose to transform. So the units are arbitrary. That should basically be, uh, yeah, yes. I agree. I don't know exactly how this thing should be stated. Like, that's kind of the problem. It's a lot of these problems that are there in the type of work that we do in this project is really to find the correct and simple characterization. Once you do that, the theorems become easy. It's a little bit like in software design. Once you have the correct class structure, the code becomes a lot easier to write. Here is the same thing. Once you find the correct definitions that are nice and they can be explained from the physics directly, then sort of the math becomes simple as well, and the things follow. So that's sort of how it works. Yeah, stating the problem the right way can often be half the solution. Here, I feel that it's like 90% of the solution. One, like this is what I think in practical ways, like a lot of these questions, right, are not well specified. Because if I knew how to specify them well, I would probably already have the solution. And so it makes this a lot hard. But anyway. So yes, so this is still an open problem, and the description is now projection as entropy optimization processes with constraints show that quantum projection are processes that maximize the entropy while keeping not just expectation constant, but all other variables as well. So this is the way that we want to recover in quantum mechanics, essentially the measurement, the projections, and all of that. The idea is that you have a quantity that you want to measure, and what you need what you need before that is you need to take whatever state that you have and prepare it in a way such that that quantity is in some sense well defined. And since we know that we have all the contextuality problem, like it's not that every quantity is always well defined. So first you have to make it well defined. And here again, the analogy is I have it here in the physical significance. The idea is that a quantum projection is essentially going from one equilibrium to another. As an analogy, suppose you have an open container of water. The number of water molecules in the container will fluctuate. Therefore, there is no single well-defined like number of water molecules. As we close the container, we change the equilibrium from grand canonical to canonical. Now the number of water molecules is well defined. And then basically, but the chemical potential is not. The idea is to frame quantum projection in the same way, that they're basically changing an equilibrium, and you go from a set of quantity that it's well defined and to one that is not well defined. And the projection, if you think it in the space of what's it called, of the ensembles, right? If you have a Bloch sphere and you want to measure spin up, right? Then the two poles are going to be the eigenstate of spin up and spin down. And anything that you can measure when you measure spin up or spin down is a classical mixture of those two, like 30% up and 70% down. And that in the Bloch sphere is just the axis that connects the two things. So what is the idea here is that whenever you have a different state, the projection is taking whatever state you have on the Bloch sphere, pushing it on the axis, and then on the axis you can say I have those are the correct probability. And that's more or less what I'm trying to do here, to sort of talk about the projection. The thing that I think is a problem, and so I'm not sure whether this can actually work, is on the continuum, because on the continuum there aren't really eigenstates of, say, position and momentum. And so I think what happens is that you're going to have the process that maximize the entropy. You are going to get ever closer to those sort of equilibria, but you're never going to actually be able to get there. And so that's sort of a problem of taking these things and actually generalize them. So the idea of eigenstate and eigenvectors and eigenvalues don't really generalize well to the continuum and try to understand what is the thing that does. But anyway, at least in the finite dimension, this should work. And so mathematical problem, we want to show that quantum projection can be understood as thermodynamic processes of entropy maximization. In a typical entropy maximization problem, the constraint is the expectation of a random variable. The idea is that the distribution over the random variable is kept constant, and this can be understood as a constraint on the expectation of all powers, right? So when you use statistical mechanics, you have some numbers and you keep those numbers. Here we want to keep the distribution over the whole position momentum constant, right? The whole position or momentum or spin up and spin down. And this also can be understood as a constraint on the expectation of all powers. It's the same thing. If you keep all the power constraint, then you're keeping the distribution constraint. And the problem is that the entropy maximization has to be, in a sense, minimal. You don't want to sort of ruin the distribution on independent degrees of freedom. And so all the entropy relative to the conjugate of the quantity being measured has to increase. And I have no idea how to specify that. And again, once this is specified, probably the result is going to be simple. Yeah. This part of your project is the most exciting. Answering this part of question will reveal many greater interesting parts. Yes, for quantum mechanics, yes. It's just that there are so many things that are interconnected to this, and my brain's a little bit shuts down when I'm trying to think about these things because it's too hard. It's hard. And but yeah, if we were able to get this done in a decent way, we would. I would basically hope that in classical mechanics and quantum mechanics you do the same thing, and then you show that thermodynamics is doing the same thing, so that all the three things are actually the same thing. That's sort of the goal, to show that there is nothing weird going on. You just have some external process that does uh, uh, you know that. Ah, mamma mia, I'm getting tired. Anyway, let's continue. Let's continue. Oh, this I think I already had an answer, but I wasn't able to actually understand what it meant. So, I think we already have an answer for this, and the answer is no, but it's like it doesn't tell me exactly what's happening. So in general relativity, space-time is curved, but it is locally flat, right? So the idea is that if you take the curvature in both space and time, it's you have a curvature, but if you get at a point, you can sort of make it flat, and then in a neighborhood, everything appear flat. And so the question is whether if you at a fixed time you can make space globally flat. So if you imagine your metric tensor, right? It would be flat if you can make it diagonal, so we have no term on the diagonal. And that you can always do locally. And so if you change points, you're going to put diagonal terms. And so the question is whether you can put all the non-diagonal term in sort of the space-time part of the metric and make it diagonal in the space. And supposedly, I did find a paper that says no, you can't do that. But it was very convoluted, so it didn't tell me exactly why not. And that's the part that I'm still missing. And but I don't have, I do not know. I should find, I'll make a note to see if I can find that paper because it should be added here. Find the paper about flatness. And I think it was a philosopher that actually gave me the paper. This is like a lot of the time, philosophers have like a more view of these weird questions than physicists have, and they know more about this stuff. And so the answer should be no, but it uh, is not clear exactly what. Uh, uh, why is that? Okay, so for a pseudo-Riemannian manifold with signature minus plus plus plus, the metric can always be diagonalized at each point. This is what is meant by spaces locally flat. In general, a metric tensor cannot be diagonalized on the whole space. We can do that only if the curvature vanishes. The question is whether the spatial part of the metric tensor can be diagonalized. That is, G alpha beta would not be diagonalized, but the spatial part would be such that Gij is equal delta Ij. So, for example, what property must a space have to be spatially flat? Okay, so if it can't be done globally, it is still interesting if it can be done on an open neighborhood at each point, and it probably cannot. So I can just remove this because if it can be done in an open neighborhood, that's something. Can you have a first? Yes, a first order expansion such that you can do that. for example, could you have a first order expansion that is spatially flat? Okay, that I don't think I know the answer to anyway. And so a way to picture space time curvature is to imagine a rectangular grid all around yourself, which gets distorted as time flows. More concretely, imagine a rectangular grid, the rectangular grid formation of spaceship. In the absence of gravity, the formation would stay rectangular, while in the presence of gravity, the spaceship would drift apart. The question is whether this picture works in all cases. That is, can we always put a formation in a rectangular grid at a particular time, or it would get distorted as well? That's basically the idea. Okay, so Tobias, I saw that you joined. Oh, this one.
Yes, I just joined.
There you go.
You about the metric tensor being flat to first order. You can
Yes.
always do this at each individual point. Expand it to first order, and then it will be flat. That's always possible. There are no constraints on the geometry.
Right. So I think I wanted to ask, then maybe it's a second order expansion. So I want to have, I don't know if you understood the problem. I want to have the spatial part flat and try to put all the curvature in the space-time part.
Well, you can make the whole 4D metric to be flat to
Right, but
zeroth and first order
at a single point.
at a single point, yes.
So now the question, can I make a, a, a second order, then it would be a second order, a second order expansion where the dependence on space is only in the time parts of the metric. That's the question.
Okay, that might be easy to answer. I remember that to show that you can get it to be flat to first order was just a counting of degrees of freedom. Like how many, if I change coordinates, like at a single point, I basically only change the basis of my tangents in my tangent space.
Yeah,
That gives me some number of degrees of freedom.
yeah.
And then I count how many essentially degrees of freedom are in my metric, like 10 for the zeroth order, and then you need to count how many there are in the first order. And then you see that it exactly matches at first order. So you have enough degrees of freedom to choose your metric to be whatever you want,
Okay.
the first order. And then you just need to count how many degrees of freedom are there in the second order. And
Okay.
then whether you have enough freedom to put everything into the space-time part.
Yeah.
It's probably not too complicated. That should be possible.
Yeah. I assume that the right person would have it, would be able to
Probably
do it.
already done, yeah.
Yeah. So can you add a link to the paper here as a preliminary? Yes, I need to find the paper. I'll look for it. It was actually a very interesting paper. It was asking a different question. It was asking about gravitational waves, and then what basically I think was the conclusion that you essentially have gravitational waves that are space-space, that you don't just have gravitational waves that appear in the space-time part. You have gravitational waves that are perturbation of the space-space part. And that basically, if you say, okay, now my geometry is spatially flat everywhere, you can't make those gravitational waves anymore, and therefore you're ruling out some things. And yeah, that was the thing. And I figure a simple static external Schwarzschild black hole might already be a counterexample. essentially the singularity was spelled right. Yeah, so as I said, like I know that this is not possible, right? I know because you can't do those the gravitational waves, and uh, um, and so now the question is whether I can do it at least as a second order. So I can basically say, okay, the metric is locally flat, and then I make a little bit of change, and now I can say that all the distortions are in the space-time. I have no idea whether this is doable or not. But again, if it is, so why I'm interested in this? Because I still don't understand the Einstein equations. I don't understand what is it that they are telling you at a geometrical level, both on basically on the relationship between the stress energy tensor and the gravitational field. Like in principle, these are tensors that have numbers, and the numbers I more or less know what they mean, but I don't know why they have to be related in that way. So I'm trying to look for ways to sort of get a better intuition that it's let's say stable in some sense, so that it's like firm to then try to understand the more complicated case. And so the simple case is, oh, everything is flat at some point. Very good. What is the next perturbation that I can make to that so that I can start having some idea. That's basically it. I know, Tobias, you studied these things a lot more than me, so uh, you know you
Well, all
probably
I
better have a
remember
better.
about the Einstein equations is basically in your Lagrangian density, you need some scalars. You have the Ricci scalar. You
Yeah,
want something that somehow resembles Newton's equation at low curvature.
yeah,
And then you can just use the Ricci scalar, and there might be higher order terms. I mean, people look at this modified gravity, where you add higher order terms to your Lagrangian and see what changes. So really, I don't think anyone has a good answer to why that is. It's just the best approximation that we have. It's like the first thing you try. The simplest Lagrangian that recovers Newton's gravity.
okay, yeah, yeah.
There's
So yeah,
not
that
much more.
that's not very very satisfying.
I
So,
agree. Yeah.
okay, then the Liouville's theorem for position and velocity. This it's one of those things that I feel somebody must have already done this, but there are a lot of things that I feel that somebody must have already done this, and that I don't see it. So we have the Liouville theorem in Hamiltonian mechanics tells you that volumes of position and momentums are conserved. And so I'd like to express that same theorem in terms of position and velocity instead of position and momentum. So what is it that happens to area of position and velocity, or what is it the analog of the thing that we're doing there? And I don't know. So the Liouville's theorem in Hamiltonian mechanics has its simplest expression in terms of conjugate variable, position and momentum. In those cases where we can express momentum as a function of position and velocity, which corresponds to the existence of a Lagrangian, one should be able to express the same relationship in terms of position and velocity. Given px, p in terms of x and v will depend on the Hamiltonian, the expression may include a reference to the Hamiltonian or to the Lagrangian when you're expressing this thing. So the Liouville theory in physical terms means conservation of number of states during time evolution. Position and conjugate momentum provide the best variables to keep that count, as the areas using those units provide a direct count of states. However, conjugate momentum is not a directly measured quantity as opposed to the kinematic momentum. So position and velocity, or position and kinematic momentum, kinetic or kinematic momentum? Oh, provide a pair of variables that are measurable and therefore provide a better connection to the physics. However, they are not canonical, and therefore the area they identify is not directly the count of states. It would be interesting to understand the expression of the theorem and of the state count in terms of these non-canonical but more physical variables. And that's basically it.
For a single particle, there's nothing interesting, right? It's just a factor of m.
Oh, no, only if you are if you have a free field, a free particle.
Because otherwise you would get the conjugate momentum would have, for example, the field, the
Yes.
electromagnetic field.
Yeah.
Okay.
Because the velocity would be so first of all, even let's say that you are not in what's it called? You are you have a free particle, but either you are not in Cartesian coordinates or you have a curvature, right? So
Mm.
essentially, your metric tensor is not the identity. Then when you go from momentum, which is a contravariant to the velocity that is covariant, you're already getting a metric tensor term there. And so the areas that you're conserving are the ones in position and conjugate momentum, not in position and velocity. And so there you're going to have some effects as well. And it would be already interesting to understand what those things are, because basically it's telling you that the metric tensor influences your count of states and therefore influences how the motion of a free particle goes around. And that might tell us something about GR as well. Because if you just do single particle with a metric tensor in Hamiltonian mechanics, just putting a metric tensor there that is not, that has curvature, you're going to get the evolution of a particle that on a curved spacetime, right? So without even having GR, it just comes out. So that might already gives us intuition there. Then when you put the forces, you are gonna have that when you go from position and momentum, the velocity is mgu for the kinetic part plus qa, and that qa is state counts or state corrections that come from the presence of a magnetic field. And so again, that would be interesting to understand what that thing is. And also it would be interesting because you can maybe understand relativistically what's happening when you transform an electric field into a magnetic field, using a non-inertial frame, right? Because stuff is going to happen there. So maybe if we had an expression of the Liouville theorem in this term, and then knowing that if you have a region of initial condition for one observer, and that would correspond to a different region of initial condition for the other observer, but the count of states, so this volume should be the same. And so maybe you start understanding, oh, when you do this coordinate transformation, states get mapped in this way, these funny things happen, you get a more geometrical picture of a lot of these things, right? That would be the hope.
Okay, can I try to rephrase? Since Liouville's theorem says that basically my symplectic form on the cotangent bundle
Mhm.
is conserved during evolution, right?
Yes.
So you want a statement not on the cotangent bundle, you want to measure states on the tangent bundle,
Yeah.
and the cos the dual vector space is related to the vector space using via the metric, right? The metric gives me some canonical isomorphism between the vector space and its dual.
Not just the metric, but also the vector potential.
The vector, okay.
Yeah. Of
Yeah,
the
in that
forces.
case, yes. Okay. But the question is essentially whether I can count states or how I can count states on the tangent bundle.
Correct.
And we expect that the metric and even more the Hamiltonian
Yeah.
somehow interferes or is relevant
Yeah.
to basically we want to extend the form or like induce a form on the tangent bundle from the cotangent bundle.
Yeah.
Okay. Yeah, that's probably something that it's probably just math.
Yeah, it
And
is.
then we just need to interpret it, but it actually shouldn't be that complicated.
No, you just have to do it, carefully. And the way that I even like to think about this is not really that you're going from the tangent bundle to the cotangent bundle, because the space of states is always the same, the space of space. The way that I really think about it, you just express the symplectic form in terms of non-canonical variables. So you are still in your space of states, whether it's a cotangent or a tangent bundle, it doesn't matter. You're just using different coordinates. And in the canonical coordinates, the symplectic form has the nice form of dx times dp. But if you express it in position and velocity, that thing is going to be more complicated. And so what exactly that thing is, and how can we reinterpret it in terms of position and velocity? And I do have some calculation of the symplectic form expressed in position and velocity. It's just a matter of taking that and understanding exactly and showing that the Liouville field theorem works there and how and so on. That's basically the part that is missing. But you're right that it's just math.
Okay, there's actually an interesting course. I think it's differential geometry or something. I was considering to take it. I don't know if it's offered next semester, but it at the end introduces also Hamiltonians and so on.
Yeah.
And that should give me lots of tools to tackle this kind of problem. Not sure when I'm gonna have time to get to this, but very interesting.
It might be the one that I audited a few years ago. I audited a class on like smooth manifolds, whatever, and this was the book that I was that was in the course. And at the end, there is some Hamiltonian mechanics as well. So it might be that same exact. Do you know who is teaching it?
I think it's Ralph Spazier.
Okay, then yeah, it was Sarah Koch that taught it when I audited it, and so yeah, there was a period in which I started auditing a bunch of courses just to that was quicker than just reading books. So. Okay, so this is the Liouville's theorem. Okay, so this I don't even remember what is it. Show the equivalence of inner product bilinear forms and trigonometry. Show this I might have already done. I didn't even know that I was had a question here. Show the equivalence of a linear space with a positive definite symmetric bilinear form and geometry of the law of cosine and suitable adjustment if the form is not positive there but still non-degenerate. Show the equivalence of a linear space with a skew-symmetric form and geometry of areas. So I think this I think already had it in my head. What did I want to do here? To really bridge linear algebra and geometry, we are looking for a connection such that the definition of each side are enough to recover the other. There are three possible cases we want to cover: positive definite symmetric bilinear form, this defining length and angles between segments represented by vector. The connection is the law of cosine by comparing c squared plus a squared equals a squared plus b squared minus 2ab cosine of alpha, with c dot c equals a minus b c dot a minus b equals ac dot a bc dot b minus 2ac dot b. So now ac dot must be ab cosine alpha. Non-degenerate symmetric bilinear form, note that for orthogonal components, the law of cosine becomes a Pythagorean theorem, c squared a squared plus b squared. If one of the direction negative definite, I think I just wanted a nice write-up for all this, because this should be all pieces that are already there. We have the c squared a squared minus b squared. This is still the Pythagorean. Oh, this is for relativity. So don't generate symmetric bilinear form, or not that for orthogonal components, the law of cosine becomes the particular law. This is the direction of it. This is still the particular theorem, except that A and B no longer represent orthogonal component. So the idea is that you express the law of cosine and find the proper connection between vectors and geometry. Okay, so this is essentially finding that if you switch the order of the so when you're expressing things like this, then this is the hypotenuse and these are the sides. And when you have when you're putting it with a minus, like the signal that you would have across the space and time in relativity, then this is the hypotenuse, and then these two are sides. And so the question here is whether if you generalize this, you would get a hyperbolic cosine instead of a sine. I think that's what I'm asking. Yeah. Do we get a hyperbolic cosine in the analogy? And then there are non-degenerate skew-symmetric bilinear form, and then this defines only areas of parallelepipeds, and this is the parallelepipeds, and this is what recovers the symplectic form. The connection should simply be that the area AB sine of alpha. Note that the sine is an odd function, therefore omega AB is norm of A, norm of B, sine of alpha, and therefore must be skew symmetric. And so why I wanted to do this, we want to make a tight connection between the three different types of differential geometry used in physics so that we can have a crisp geometrical interpretation for the physics. The first case is used in standard physical space. The second case is in space-time. The third case is used in space-space. An important aspect here is showing that the assumption of the existence of the specific form with specific property are equivalent to the geometrical and therefore physical assumption. Okay, so that's basically when I was trying to think more geometrically. Another issue is that mathematically, these are usually treated as different subjects. We believe it is useful to see them as variations of a general theme so that one can build a more general intuition for the tools that are common. Okay. Sure. One of the things that I have been struggling, and I'm still struggling, is that there is also a relationship between this same thing and the triangle inequality, because the biggest that this can be is when the cosine is -1, and so now this becomes a square, and you're gonna get the triangle inequality, and so that a square plus b square is always greater or equal to c square. And that's something that I need to prove in some form for the entropy, because the entropy gives us, in the end, all these three geometrical things. I'm starting to understand that they actually come from or are equivalent in some sense to how the entropy works. And there is a distance function that there is the Jensen-Shannon divergence that it's proven both in classical mechanics and quantum mechanics to essentially be the square of a distance, but I'm still not able to prove it generally. So anyway, geometry and everything. Okay, fine. Let's keep it like this. And the last thing that I had is okay. This is part of what I was saying before. This whole notion of generalized what's it called? Generalized ensemble spaces. And as I said, next time we are gonna probably start reviewing the things that I already have there, because I think it's nice if I get feedback. So a recurrent idea in our project is that ensembles are the prime physical objects, while pure states are abstraction. The goal then is to find the minimum set of axioms for that idea, for that area. What? The goal is to find a minimum set of axioms that are always justified for statistical ensemble. Classical mechanics and quantum mechanics should be spaceization of such spaces, confining at, and this is the part of the ensemble spaces. We found appropriate axiom for convex spaces, which an ensemble space can be shown to satisfy. The idea is that one can always create affine combinations of ensembles pi, ensembles xi. So these are the sum of the pi with the xi, as long as the sum of the pi, oh man, this was really not proofread, are equal to 1, whether ensemble spaces always embed in a vector space is unclear. Instead, it's clear now. They always do, as long as the entropy exists. Classically discrete spaces correspond to simplexes. Classical continuous spaces correspond to the space of differentiable functions defined over a symplectic manifold, which also integrate to 1. Quantum spaces correspond to the space of positive semi-definite Hermitian operator, which trace 1. We're still looking for the appropriate axiom for entropy, for subspacing, and the other characterization. Yes, we're going to look at all of this. The convex combination represents the statistical mixtures. The photon ensembles as basic object is explained by the reproducibility of physical law. A law, in fact, never applies to a single case, but establishes whenever X we have Y relationship. Therefore, the objects must be repeatable procedure of measurements and preparation. This means that X and Y must be conceptually ensembled. Okay, so these were all the pieces. And I don't have anything else. So,
Can I ask about this one? The
yep.
combination, just a technical thing.
Yeah.
That's an affine combination.
Mhm.
That's doesn't that mean that I can have 2 points and I can get like the whole line that is going through these points, or
Correct.
only in between these 2 points? You know what I mean?
Yeah. So, so imagine that you have two vectors, right?
Yeah.
If you take all possible linear combination of those two vectors, you get the whole plane.
Yes.
An affine combination, it's where the coefficient sum to 1, but they
Yes.
can be any number that you want.
Yes.
At that point, you get a line.
Yeah.
It's the line that connects the two vectors. A convex combination, instead, the coefficient have to sum to 1 and be non-negative.
Yes.
And so you only get the segment between the two.
So don't you want a convex combination and not an affine?
Correct. We are going to get convex combinations.
The idea is that one can. I'm just reading the text. Why do you talk about affine combinations in this context? You can always create affine combinations.
No, because it was a mistake. Thank you.
Okay. So we need the other condition that they sum to 1, but they're also all positive, right?
Yes.
Okay. And then the thing is we can extend the space, then we have also affine combinations, but they are not physical. And we can also
Yeah.
allow arbitrary linear combinations and embed it in a vector space. That's also unphysical, but doable.
Right. So
Okay.
the whole problem is the finite convex combination are the things that you're guaranteed to have.
Okay.
Anything else you may or may not have. So you may have an infinite convex combination or not, because you may or may not have the limits. To give you an example, there are probability distributions, so things where the pi sums to 1, so it's a convex combination, that do not have an entropy well defined. The entropy will diverge.
Mm-hmm.
Those are not things that we're going to want.
And that's
Right?
related to infinite convex combinations.
Right. That would be infinite convex combination.
Mm-hmm.
In classical mechanics, you can get away with saying that everything is a convex combination of some precise, at least in the limit, things. In quantum mechanics, you're not going to be able to do it. because the two-state system is a ball, and even if you get 4 points, right, in the ball, you can only get a tetrahedron that connects them through
Yeah.
convex combination. You're not going to get the whole ball. And so if you want to get the others, you, for example, will need a fine combination so that you can go outside of the convex structure. And this is why you have in quantum mechanics, you have negative probabilities.
Yes, and if you try these, what are they called? Wigner functions and so on?
Yep.
Okay.
So all those things are basically because what happens is that the space and then we'll start seeing it the next times. I was able to show that you have if you have basically we're going to have three things. We're going to have the topology that tells us what we can prepare and what we can measure. And the topology is the only thing that works with limits and infinite things. Then
Yeah.
you have the convex structure that is always finite. You can always make finitely many convex combination of finitely many things. You can make mixtures of finitely many things. You can always guarantee with that. It's going to be the topology that tells you which infinite things you're going to be able to do and which you can't. And then you're going to have an entropy, always well defined on each element. And the existence of the entropy makes this whole space a vector space and defines the geometry. It gives you a notion of distance, it gives you a metric tensor, it gives you a bunch of things. One of the things that it does, it also bounds the affine combination. So you know that now you have a convex space that is embedded in a vector space. But you also know that if you take two elements, two ensembles, and you make affine combinations, and you look for the ones that are actually ensembles, they are going to be on a finite line. Like they can't go to infinity on one side or the other.
Mhm.
And therefore, the whole thing is understanding once I know that some things some affine combinations are actually ensembled. What other things I can say? There is a whole host of things that I'm trying to clarify my head in these terms. But a lot of things I've already done, and I think they're mathematically sound. So that's why I think it's worth starting to review them.
Okay, so you wanna go start the from the beginning of ensemble spaces and show what you've done so far.
Yeah,
I don't know much about it yet. I like the general theme I understand, but
I assume
you
that
didn't look at the
nobody in the
details.
live will know anything about it, so we're gonna be slowly and go through the definitions that are already done and try to. And in fact, part of the feedback for me is seeing what the diagrams might help people to sort of get where I'm at in the shortest amount of time.
Yeah.
Because I already went through a lot of cases, corner cases, and I already like junked a lot of other things that could have happened, and so I need to be able to put this in a form that is digestible and quick to. So that's kind of why I think it's more valuable for me to do that than the quantum mechanics section of the book, because here I already have like ideas that are like very mature. I have theorems that I've proven. Like the we might even be jumping to the information geometry and entropic geometry part first, because that's the part that I have most stable. And so we're going to jump around. We'll find the sections that I already have well developed, and we'll go through them slowly, go through the proofs, make sure that I haven't missed anything and stuff like that. Does it make sense?
Yeah, does it? Yeah, that makes sense. It's like I really enjoy constructing mathematical structures, but they look so natural. So when you construct them yourself, they look so natural. But whenever I try to show to someone else, it's like so all the idiosyncrasies that I put into them, they show up whenever I show to someone else.
Yeah.
So yeah. And by the way, does the ensemble space build on top of the topology on like does it need the structure of the topology beforehand, or does it start from somewhere else?
What? Can you
So
repeat?
do you is the structure of the ensemble space built on top of the structure of on top of the topology?
Yes.
Okay.
Yeah,
Okay.
yeah. We're gonna have you're familiar with the experimental domain. That it's basically
That
gonna be an
part,
experimental.
actually, what I'm not familiar with is what exactly experimental domain, theoretical domain is. I have like a vague idea that you extend, I think you extend the topology to the sigma algebra,
Yeah,
and then you get the theoretical statements,
yeah,
and that's where you can then define probability distributions on.
yeah.
But there are some more details which I don't fully understand yet. I'm not sure if it's necessary.
They're not. If you want, and if other people want, we can go through them anyway.
Yeah, I really like this part. And I think I just need to see it again. It's not that complicated, but it's not at the front of my mind right now.
Okay, we could have for the next time then just a review of the whole logic and tests and testable things and how they connect to topologies and sigma algebra.
Yeah, that's very nice anyway to look at it again. I think it's the nicest structure that you have so far.
Oh yeah, it's completely clean. Like that
Yes.
thing, it's like a joy. It's like so nice and clean, and everything makes sense. Like that's what sort of convinced me that we can actually have a real mathematical structure for all of physics because I was able to do that. Yeah.
Yeah.
And now I'm just doing the same thing for states and ensemble. Like and it's gonna be the same squeaky clean because it's getting there.
Yeah, sounds fun.
Yeah, the part of the topology, it's like a little bit more abstract, but this part is going to be very concrete. Okay, so WKK, you confirm that you also want to review that. Yeah, okay, let's do that. Next time we're going to go through in principle, it's a part that I also wanted to make videos for. And I started, but then it takes a long time to make videos. Yeah.
Yeah, sounds good.
Okay. Were there like looking away from poorly defined notion like quantum. Yeah, so I agreed, WWKK, that in quantum mechanics, in classical mechanics, you can get away without thinking about a lot of details also on the conceptual side of physics. And quantum mechanics instead forces you to be a bit more careful. And unfortunately, like that's the part that we haven't done. Like in physics, we just get this mathematical structure, do some things, get results. But I think we haven't confronted the real thing that we need to confront at the mathematical level, well, at conceptual level. Then the conceptual level maps to the math, and then you get the math and run with it. Okay, so I was thinking, okay, I don't know how we're gonna do it. We just open up the book and just go through it because I don't think I will have time to prepare anything, or I'll just talk and then see where we get. Is that what we're gonna do?
Yeah, use the book as it stands for a guide. That's a good plan, I think.
Okay. Very good. Any other questions or things before it's early, but I also have to go away early, so I think it's good for me anyway. But if there are questions on anything, I'm happy to chat.
I don't have anything specific right now.
Okay, so yeah, I was just waiting for the
Yeah.
chat more than you are live. The other ones are like 20 seconds behind or something.
Yes.
Okay, so we'll just close and thank you everybody for following. See you next time.
Bye.
Bye. That's the thing, and this